So now I'm starting recording. For folks that are watching the Zoom lectures, sorry, you may want to look at the YouTube ones instead. It might be slightly prettier. Okay, so last time we talked about buffer overflow attacks. Today we are going to talk about defenses, and really our goal is to understand how to mitigate buffer overflow attacks, the trade-offs of these different mitigations, and then how you can actually bypass these mitigations if you were an attacker trying to carry out real-world attacks. Okay, so the simplest thing maybe we'd want to look at is can we just actually avoid writing C code that has buffer overflow bugs, right? And this would be super awesome, but this is actually kind of challenging, right? So the intuition says okay, well, let's just avoid using unsafe functions. So if we have strcpy, strcat, gets, and all these things, we can maybe even get the compilers to scream at us when we're doing bad things. And we're clearly actually doing this for real, right? So your compiler is definitely screaming at you when you're trying to use gets, right? So this is a great idea. The problem is, we have to go and change a bunch of code out there. Two, you write your own code, right? You're not always relying on these library functions, which means that you may be introducing these buffer overflows in your own code, right? You can implement your own strcpy. Nobody's going to stop you from doing that. And what that means is basically we have no guarantee that we found everything, and unsurprisingly, people miss quite a few of these places where there are buffer overflow bugs, and we're back to square zero. Okay, but suppose that we were willing to actually be more defensive. What should you actually do? Well, the thing that I would recommend you do is not use strcpy, but use things like strlcopy. You might have gotten advice to use things like strncopy, which basically takes an additional argument specifying the length of the string. That one's not bad, but it's also error prone because it forces you to think about the null byte at the end of the string. Whereas the BSD versions, the strl versions, they're actually slightly better because they actually insert the null byte at the end, right? So if you're going to rewrite your code, those are the things that you should use. If you're writing new code, those are the functions that you should use. But just to kind of hammer home why it's so tricky to use these safe alternative functions, I want to just look at printf, right? This is the simplest thing we can possibly look at. So let me give you a quick poll on this particular question, right? So what I'm curious about, if buff, and let's actually just avoid the simple case. Let's say buff is actually null terminated, so there is a null byte at the end, right? If buff is under user control, is it actually safe or not? So why don't we do a vote instead of saying out the answer? Or I guess, okay, well, never mind. Just scream out the answer, because apparently the polling doesn't actually like what I'm trying to do. All right. that's a lot of no's. All right, you're right? So it's not safe, right? Okay. What about this? Right? Is this safe or not? Oh, sorry. So this is actually safe. All of you said no, but it is actually safe. I take that back. Right. So to the original question, this is actually safe. So if the string is null terminated, then our guarantee is that we're going to start reading from the beginning of buff, and we're going to print until the null terminated string. So this is actually okay. I'm glad you all said no. Right? But okay, is this version safe or not? Right? And again, this will be null terminated. So all the buffs that we're going to talk about are null terminated. Right? Okay, so all of you are saying no. Great. So why not? And if you want to speak up, you're welcome to. You can raise your hand if you want, but I'm also okay. Yeah, great. So, what's the first argument that we pass to printf? Well, it's a format string that we then, within printf, interpret and look at other arguments, right? So what would be a bad format string I can pass? Well, I could just pass, printf, my own evil format, which might be, read the next thing the next argument, the second argument that's on the stack, and then read the third argument and treat it as let's say I'm gonna just say %d um, as an integer, and so on and so forth, right? So like basically, if we give printf a format string, it starts interpreting these things, and based on this string, it starts actually looking at what's on the stack, right? The next argument. So, and if we don't give it other arguments, which in this case we don't, it's going to read past the stack. Okay, so why is the previous slide safe? Right, so the reason it's safe is because we're actually treating the first argument as a string, right? And as long as it's null terminated, we start reading from buff 0 until buff 55. Let's say if 55 is the null byte, right? So this is actually an okay way to print untrusted strings, as long as like you do %s and you make sure that it's null terminated. So make sure that buff is actually null terminated. If it's not, you have other problems because you can keep reading. Printf will keep reading until it hits a null byte, right? But as long as it's null terminated, then we're good, right? Okay, so here, this is under the attacker control. So the attacker can pass whatever they want. As an attacker, what I would do is I would pass in a format string, because a format string lets me read other parts of memory, namely things on the stack. But you can also perform writes, right? So there is the really cool %n. If you haven't seen this, just look it up. I'm not going to talk about it here, but this actually lets you write to parts of memory. In particular, it lets you write like the amount of bytes that printf has so far printed out. So if buff is long enough, you can do all kinds of like super interesting things. Okay, so I think we've already answered this question. The answer here is that this is not safe, right? Because there's no attacker here, but basically, like if the attacker had given us just this particular string in the previous slide, right, we would be reading the next argument, which is the bottom of the stack, and we just keep reading onwards and potentially leaking whatever is in memory until we hit null bytes. Okay, if you're super curious about these things, I recommend looking at this paper. It's a really nice paper. It's called Exploiting Format String Vulnerabilities. Basically, printf is Turing complete, so you can read and write memory and do whatever you want to hijack control flow, right? And there's lots of exploits that you can write using just format string vulnerabilities. Okay. Kimia, so did I answer your question earlier? So how does the attack pass their own format string, right? It might be just an input that you take and then pass it to printf because you didn't think more carefully about how that might behave with printf. Okay, awesome. Okay, so I guess we're at the point where I hope I've convinced you that we can't, write correct C code. So what can we actually do? Well, maybe we can actually, if we can't prevent, a developer from writing buggy code, we can maybe prevent or mitigate the exploitation of these bugs that we've exactly damage control. So we could maybe prevent the exploitation of these bugs. And we're going to look at a few different ways of doing that. In particular, we're going to look at stack canaries. We're going to look at separate stacks and safe stacks. Then we're going to look at WXRX, which is memory writable or executable. And we're going to look at ASLR. So we're going to look at all of these in the rest of the class. And kind of these are things that are actually used in practice. Pretty much anytime you run a process, it has at least these things. This is kind of cool and new, but it depends. It's something that you'll probably have in future processors. We don't really do it now for a lot of things, but if you're using WebAssembly, for example, you get this for free. But these are on by default. And if you look at our examples or our assignments, we actually turn these things off explicitly because our attacks wouldn't work as well. But we'll see how to actually bypass these as well. Okay, so let's start with stack canaries. What are stack canaries? Well, to understand what stack canaries are, we basically have to go back to kind of the old days where we basically need to understand what a canary is, right? So if you haven't seen what a canary is, I suggest looking at the Wikipedia page. But anyway, canaries are really cool birds, and they were used. I don't know. I hope they're not still used. I don't think they are, but they were used in the early 1900s to detect whether there was carbon monoxide in a coal mine, And if there was, like you tell the miners to get the hell out because they've clearly hit um, something they shouldn't, right? So like, how does this actually work? Well, it turns out that these things die, and if you see a dead bird, you get out. So it's kind of sad. But basically, that's what happens, right? So like, if the bird is dead, well, at least people aren't dead, so you can run. But I don't know. As humans, we're kind of like pretty weird. So arguably, humans who might have gone there first. Um, but let's not go there. Okay, so what are stack canaries? The idea of stack canaries is similar to um, the miner's canary, and what we're going to try to do is we're going to try to prevent control flow hijacking by detecting buffer overflow. So we're going to detect whether or not a particular buffer overflow has been triggered, essentially. So whether or not somebody's actually trying to exploit this particular buffer overflow bug. The way we're going to do this is we're going to place a canary between the local variables that and on the stack frames to protect essentially the return address, right? And then when we get out of the function, we're going to check to see like, hey, has the canary been overwritten? If it has, then we know that our buffer was overflowed. So we should not continue because the program might actually return to an attacker controlled return address as opposed to the original program intended return address, right? And we're going to insert canaries. I think my camera keeps doing weird blurry things. We're going to insert canaries in function prologues, and we're going to check them in function epilogues. So let's take a quick look at the example that we saw last time. So last time we had our stack frame where we had, so here what I'm looking at is this function here, func, right? So we have our buffer and we have our local variable c, and in between that and the saved EBP and saved EIP, right? We're going to insert a canary, right? So this is going to be a special value. And here's what it looks like when we compile that code, right? So we're doing like more than what we saw before. So this is the code, the original code without stack canaries. So that we explicitly turn them off. When you turn them on, a bunch of things actually happen, right? So if we have this flag passed to GCC to fstack protect strong, it's going to write a canary in the function prologue, right? So the canary is stored at this address. This is somewhere in the GS segment, and it's written to the stack to this particular address, -12 EBP. And then when we exit the function, we're going to compare what's on the stack with whatever is at that same location where we have the canary. And if the check fails, we're going to call this function stack check fail and exit the program because something bad has happened. Great. So that's a great question. So like, does the canary have to be random? If not, can they just build it into the attack string? We'll talk about this. But before we talk about that, I think the things that we want to like think about whenever we're deploying mechanisms like this is what are the actual trade-offs, right? So first, if we look at how you'd actually implement stack canaries, well, you would do it in a compiler pass. So this is actually pretty cheap, right? Like as the developer, don't have to modify my code to take advantage of this new mechanism. I just have to recompile it and now run the program, and I get the benefits of stack canary. Now, the downside is each of these protected functions are actually more expensive, right? The function call is no longer, just saving EBP. Now we're doing quite a bit more things, right? Like we're particularly reading from memory, writing that to the stack, and we're going to, again, read from memory and from the stack and compare those values on the epilogues, right? So each function entry and exit is now quite a bit more expensive, right? So we've added quite a few more instructions. And we want to think about what is this actually giving us, right? So let's think back to day zero, right? Where we have, where we want to think about how you would go about attacking this by thinking outside of like what the assumptions of the systems are, right? So the assumption of stack canaries is that it's impossible to subvert control flow without corrupting the canary, right? Now, is this a good assumption? How would you bypass this assumption? Right. So great. So I tried to jump over the canary. Maybe we can try to figure out what is the canary. Um, can we have a fake canary? Maybe. But at least those two, right? So okay, like A, well, okay, this itself might not be true, right? So for example, I don't have to overflow a stack, a buffer that's stored on the stack. I can overflow a function pointer somewhere else on the stack or the heap, right? It doesn't have to be in the current stack frame. So if I can overwrite an arbitrary pointer, I could just hijack the control flow, assuming that function gets called, and then I'm good to go, right? But this is kind of cheating. So in practice, this is actually very practical. This is kind of how you usually carry out modern attacks. You actually have what are called like write gadgets, and these write gadgets lets you write to arbitrary parts of memory, and usually you'd find a function pointer somewhere in the address space, and that's where you would write the gadget and then hopefully call the function indirectly through some function pointer. What we're going to look at in this class is these other three ways of subverting stack canaries, right? So the first one we're going to look at is called pointer subterfuge, right? So, and then we're going to look at how we're going to learn the canary. So let's start with pointer subterfuge. So here I have a slightly different program. It's pretty close to the one from before, but it has a few more things on the stack. So first, the thing that I want to point out is that we have here some pointer PTR, and this takes some address to I here. That's the first thing that we're going to do when we run this function assigned to that pointer. Then we have some value. Again, it's just some local. So if we look at the stack, this is what it looks like. We have the address of I and 44. Then we have our buffer. Then we're going to have our vulnerable stir copy, right? So we're going to overflow the buffer. When we overflow the buffer, we're going to overflow, val and pointer. And this can be kind of ugly because the next line assigns val into pointer, right? So this is essentially giving us a free write gadget, right? As an attacker, I can overflow the buffer to write arbitrary values to arbitrary parts of memory. So let's actually do this. Okay, so we're going to start by first just our goal is basically to hijack control flow. This is easier than in a real attack. But what we're going to do is we're going to divert control to function foo. And here I picked an address for the start of function foo, which is 0x0804 9 blah blah so on 95, right? And I'm going to give this part of the stack, so where the saved return address is, it's 0xFFFD09C, right? So our goal is to essentially overwrite the return address to foo. And then when we exit function func, we're going to jump to foo. So how do we do that? Well, we overwrite the buffer as usual, right? But what we're going to write in this slot here, where val is, we're going to write the address of foo, right? And where pointer is, we're going to write the address of the EIP, right? So what happens when we execute the stir copy? Well, it's actually not even going to overflow into the canary, right? Like we're just going to leave the canary in place, so that's going to be great. But then we're going to execute this line. What does that line do? Well, it writes to where pointer points to value val, right? In other words, we've overwritten this part of memory to point to the start of foo, and then when we exit the return, we're done, right? So we've managed to hijack control flow without subverting or overriding the canary, right? Okay, so what we looked at is how to overwrite a local variable, two local variables, really. One that is a pointer, one that is just a vanilla value. And that essentially was an arbitrary write gadget. That thing is super powerful in an actual attack. But you might have cases where, say, you can just hijack control flow directly. So like if I have, say, function pointer stored on the stack, like I do here, right? So here, f pointer is a function pointer, and I have it point to bar. And I call that function somewhere down the line, in particular after the buffer overflow. then one thing that I can do is just overwrite f pointer to point to my desired function. And now instead of calling bar at this line here, we're going to call, pwn. And we're going to do the same thing, or we can do the same thing when we have, say, function pointers as arguments, right? And this is more common than you might think, right? Like if you think about, say, the qsort function in C, right, that thing takes a function pointer, right? If it has a buffer overflow, suddenly you can exploit qsort to jump to whatever function or part of the code base that you want, right? So this is pretty cool. So canaries are awesome, but we don't even have to clobber canaries, or at least our assumption that the only way to hijack control flow is by overriding the canary is definitely false, right? But we want to get the best or the most out of canaries that we can. So how are we going to actually fix this in a real program? Where if we look at what's actually going on, well, we're overflowing locals and arguments. Like when we do that, that might sometimes allow the attacker to hijack control flow, right? So what can we do about this? Well, one thing we can do is we can move the buffer from here, right? It's at the bottom of, or at the top of the stack. We can move it near the canary, right? So now I know that if I overflow this buffer, it's going to overflow the canary, right? Okay, that might not help us with our arguments. So what we're going to do is not only move the these buffers to the top, we're also going to copy arguments to the top of the stack, right? So now overflowing the buffer means that it won't touch our local variables and our arguments, and at least within this function that we're executing, the integrity of the local variables and arguments is preserved. Right, like that doesn't mean that you can't overflow into other stack frames, but now you would have overflown into the canary, which means that you'd clobber the canary, and unless you somehow figured out what the canary is, we will be able to actually detect this attack when we exit the function and execute the function prolog, which checks this canary on the stack against the reference canary that's in memory. Okay. Right, and I think I want to point out, like I said at the start of this, is your compiler actually does this. There are different modes of turning on canaries. For example, you can use fstack protector. This turns on stack canaries for functions that have character buffers that have a size that is reasonable enough for an attacker to use. So like GCC's default is like if you have a stack allocated car buffer of at least length 8. Then we're going to turn on stack canaries. We're also going to turn on stack canaries if you have any variable sized, stack allocations with alloc A. You can be more paranoid, so you can turn on fstack protector strong. This additionally actually turns out on stack canaries for functions that have local arrays of any size or any type, not just car buffs. And particularly because, so this one is essentially tailored for classic attacks or like string-based attacks that depend on cars being read from untrusted locations, but you can totally mem copy things into buffers that have very different types, and that could also be pretty bad. Those can overflow as well. With fstack protector strong, you also get stack canaries if your functions have references to any local stack variables, right? So if you take the address of a local variable, we're going to turn on stack canaries. And again, the reason is kind of like what we saw earlier, which is if you do that, then you might actually kind of expose some write gadget. We'd be writing to parts of the stack that, might not be covered by overflowing alone. Okay, and if you turn on fstack protector alt, you get all the functions, right? So if you look at all of these, they turn on different, the function prologs are much bigger than, as we go down, and this expands to more functions, right? So the amount of overhead that we're going to pay performance-wise is going to be higher the more stack canaries that we use, and kind of Yeah, I mean that's actually all. So the more functions you have, the more overhead you're going to pay for stack canaries if they're turned on by default. Okay, so let's look a little bit at a piece of code that you might actually see when you compile the function that we saw before, right? So if we look at a typical function prolog with the strong mode turned on, what do we do? Well, the first thing that we're going to do after we um, save EBP and adjust ESP to the top of the stack, we're going to copy the first argument, second argument, third argument. Then we're going to write the canary to the stack, right? So we're doing quite a bit of work before we actually execute the useful pieces of code. But this is actually pretty useful, especially if you're executing kind of classical code that is prone to these kinds of bugs. Okay. Now with my attacker hat on, I want to think about like, why do we copy references? What is a reference? So we copy arguments to the bottom. Yeah, so we copy arguments to the bottom because we want to make sure that they're not clobbered, right? So if we look back at a few figures down, let's see. Yeah, here, right? Let me, I guess, clear this. 2 seconds. Okay, clear page. Right, so on the left side, we have the original function. So if we overflow this buffer, right, we're going to overflow the local variables. So if those local variables are used as pointers, that could potentially allow us to hijack control flow or write to arbitrary parts of memory. But we'd also be able to write past the canary into the arguments, right? So we could potentially overwrite arguments. If those arguments are used in the function, again, we've overwritten them and we won't detect until the end of the function return whether or not these arguments have been overwritten. And if we use them again as pointers, we could potentially hijack control flow, right? So by moving it here, we essentially say, okay, well, these things can't be mucked with if we overflow that buffer. Okay, awesome. Exactly, that's right. Okay, so we're attackers. We're going to think about how can we defeat stack canaries. So we already saw pointer subterfuge violates at least the assumption that I have laid out here. And then we're going to look at another one, which is, which kind of depends on how we pick canaries, right? So let's talk a little bit about how we pick canaries. And I think this was brought up at the beginning of when I mentioned stack canaries. So how do we pick canaries? Like, what are those values? What do they look like? Well, like one thing we can do is we can be pretty clever. We can pick something like, OXOOOD OAFF, right? And if we look at what those are, what they actually mean is the null byte, then we have carriage return, new line, and -1, right? And if we say as an attacker, even if we know this stack canary, right, it'll be really hard for us to carry out a clever or a useful attack because we'd be, writing null bytes, carriage returns, and new lines. And when we pass those to stir copy, we can't overflow past that, right? Like stir copy or gets, they stop at the null byte. Right, so that's pretty great, right? So if we pick these clever values, we're pretty good. You might also want to pick these canaries statically because you can optimize the code that you're generating, right? So instead of looking at like reading from memory to figure out like what the canary is and write that on the stack, you could just write a constant to the stack and you can check what's on the stack against a constant. So you're at least saving a few memory operations per function called an entry. Let me try to see what the questions are. So we compare our reference canary to the value of the canary on the stack to see if you got hijacked. Yeah, exactly. Well, so how does that actually prevent the hijack? Great. That's a good question. Let me draw the little stack diagram that we had before. So we have our canary here, right? And we have our saved EBP here and then saved EIP here, right? So if we clobber the canary, right, our whole goal is to overwrite the EIP so that when we exit the function, we jump to this address that we wrote on the stack, right? Right. So like our goal as an attacker is to overwrite the return address to hijack control flow, right? And if we're going to successfully overwrite this return address, well, if we use a buffer overflow with, like, say, through stir copy or gets, we're going to also overwrite the canary, which means that before we actually call ret, right, we have our epilogue, which first checks whatever this value is on the stack against the reference canary, and if it doesn't match, we're not actually going to like call ret, right? We're not going to return out of the function. Instead, we're going to bail out of the program, right? So we're going to call that function that basically says like, hey, everything is screwed up. Please exit, bail, bail, bail. Right. So I'm going through things a little bit quick, but we already kind of saw how you would defeat this, right? Like this isn't necessarily always going to help you, but it will actually catch quite a few stack overflows that would otherwise be almost trivial to attack or take advantage of. Okay, great. So right, like if we have a gets, well then we know that we're not going to be able to like write a useful value into the canary, and we're essentially as an attacker, we're going to be stopped before we even get to the point of return. We're going to be stopped at the point of the stir copy, right? Like we can't write something useful there because the stir copy will only copy up to this bit, some part. You can't quite see that, but some part of the canary, but not the whole thing, right? It's going to stop at that 0. So we're only going to be able to overflow it this much, not past into the return address. Right, because our goal would be to say, well, okay, I'll actually write the canary value on the stack, OX00, D0, AF, but that's when stir copy actually stops because we've given it a null byte. Okay. In practice, we don't actually use these clever values, but sometimes these clever values do appear in the canaries that we generate. And typically we generate canaries randomly. And we'll talk a little bit more about how you'd actually bypass those. But even then, right, we might have zeros. And even if I somehow figure out what the canary is, writing a 0 basically is impossible if our exploit depends on a stir copy or gets or a string style vulnerability. So where is the reference canary value stored? That's right. So if we picked these, constants, they would just be constants. But what I showed you earlier in the prologue is that they're actually stored in memory, right? So they're stored at, GS20. So if we look back at this figure here, right, this is taking the canary out of this memory address here, writing it into EAX, then moving it from EAX onto the stack. So this is in memory. So you can definitely overwrite both the reference and the actual canary, but you'd have to have, a gadget that lets you write to GS20, which like is already super powerful. So you might as well just write, to the return address because, well, that's more useful. But we're gonna also see how we're going to learn the canary and figure out how to write the right canary automatically. Okay, so here we were talking about picking clever values, or at least some of these appearing even in randomly generated canaries. The thing that I want to point out is, even though we're talking about strings and string style vulnerabilities here, you can have a mem copy, right, which doesn't care about the contents of the strings overflow, right? So, and this example here, I have a mem copy that copies from stir to buff, and it copies, the length of the string. Well, if stir is attacker controlled, we can definitely go past this 1024 byte boundary, right? And we can overflow into both the canary and the return address, and mem copy doesn't stop at the null byte. So, if we were being clever, that then actually worked out super well in our favor. And as an attacker, I could now just take the canary value that was static and just have that be part of my exploit. Like in this case, string, but it's not really a string. It's treated as, just a bunch of bytes. Okay, right. So what we ended up is that we should pick random values. Now, the question that I have for you is, when do you pick a random value for the canary? Great. At runtime. When at runtime? Yeah, on the program start, right? Like you could imagine being more fine grained, but at the program start, like one of the things that we do is we generate a random value, and then we're going to use that throughout. We don't do it on a function call basis because that would be pretty expensive, right? Calling a the random number generator on each function call would now make each function call, like 10 times slower, and we already made it, like 5 to 10% slower. Um, but that you can imagine that actually helping, because that would make certain attacks that we're going to talk about later quite a bit harder. But if you're thinking about like, what am I actually getting for this, when we might have pointer subterfuge style exploits that we can just use and completely sidestep like what stack canaries actually give us. Okay. Now, even if we do pick it per function, well, I guess that would get pretty weird. But at the start of the program, we might still be able to learn this canary, right? So it's random, but we can actually learn it in certain settings. And what we're going to talk about is servers. But like before we talk about how you do it for a server, the thing that I want to briefly mention is, like in a real attack, usually you chain a bunch of vulnerabilities together, or you chain a bunch of exploits that exploit, a few vulnerabilities. So, okay, like what do we need to carry out a control flow hijacking attack if we have stack canaries? Well, we need maybe one vulnerability to read arbitrary parts of memory to basically read the value of the canary from GS20, right? So that would leak. We essentially need a vulnerability that is a memory disclosure. And then if we have that, and we have a second vulnerability, where the second vulnerability is just, say, a stack overflow, now we can chain these two together. So we're going to use the first vulnerability to figure out, like, hey, what the hell is that part of memory where the stack canary is saved? Give me the stack canary. Then we're going to use that as part of our payload to the second exploit, where we actually perform the stack overflow. Right. So this is like, all we need is two. In practice, if you look at like real systems, things get way more complicated because we're going to have sandboxes in between, and like you might need on the order of like 14 vulnerabilities to carry out like an end-to-end attack. But these are like, we're talking like nation state attackers. Carrying out an attack against somebody that's less specific, you could probably get away with just a handful. Okay. So what we're going to look at is a slightly less intense and less clever attacker, and we're going to look at it in a particular setting, namely web servers, right? So in a web server, and here I'm talking about, say, Apache 2. If you didn't do the reading, I recommend taking a look because it's actually a lot of fun. But the basic architectures of these web servers is we're going to have a main server process. This thing establishes a listening socket, and then whenever we get a connection, we hand off that connection to one of 10 workers. Let's say if I have 10 cores, right? So I have multiple processes, and they all handle different requests from different users. And because I want my server to stay up, if it ever dies, and it might die because it crashed for like one reason or another, then what we're going to do is we're going to fork another worker so that we can keep our server, going and servicing, the millions of awesome users that we have. Now, each of these worker processes, they accept the connection on the listening socket and then just handles the request, right? So this is going to be kind of awesome, or at least we're going to take advantage of the fact that like these servers always respawn these workers whenever they crash. Now, to carry out the attack, the thing that we need to know is that whenever you fork a process, right, the memory layout of that child and the parent is going to be the same, right? So what that means is if we look at, GS20 in my child, it's going to have the same value that I have as the parent, right? So like we're basically going to be sharing canaries, right? And we're going to do this time and again, right? So whenever we crash, we're going to get a new process at that GS20. We're going to have the same value, right? So the canary is not going to change across forks. Okay. So as long as we're all on the same page, right? Like the canary is shared across children. And because these servers restart any crashing process, we're going to have the ability to essentially crash the server as many times as we want to essentially brute force and try to figure out what the canary value is. So let's actually do this. It's actually quite a bit of fun. Okay, so here I have what my stack looks like. I have, some buffer where we're going to take the user request in, and then the stack as usual. Well, within this like service request function, I have the old saved EBP, the saved return address, and so on, right? So this is just a normal function that handles requests, and it does so by reading, the untrusted requests from some random person on the internet. So what are we going to do? Well, the first thing we're going to do is we're just going to overflow this buffer with our beautiful AAAA, right? So it's just going to be a bunch of 4 1s that we're going to see on the stack. Okay, this is great. So if we do this, and we know that like at least up to this point, our program is likely not going to crash, right? Because we didn't overflow into the canary. Now, right, so this is a lively program, works perfectly fine. We might get a response back from the web server. Now, we've essentially figured out what the size of the canary is, or at least we can figure out the size of the canary by essentially just giving it more data. So if, say, we pass in 4.1, right, now it's going to overflow a little bit into the canary. So instead of bad cafe, we have now bad caf 41. Well, when we return out of this function, what's going to happen? Yeah, we're going to crash, right? It's going to crash because we're going to check what is the canary that's stored on the stack against, what's in GS20. GS20 has bad cafe. That doesn't match up with bad caf 41, so we're going to crash, right? And great, now we know what the length of this buffer is. So we know kind of like how much of just the canary we've overflowed on our first crash. Now, what we're going to want to do is we're going to try to figure out like what is the actual canary. So what are we going to do? Well, we're just going to pass it different values. So instead of OX 414141, we're going to give it 414141, but the byte that goes into the canary is now going to be 42. Right? Okay, what's going to happen now? Well, it's going to crash again. Right? So what are we going to do? We're going to do 43, 44, 45 until we get to FE. Once we get to FE, our program doesn't crash. We guessed at least one byte of the canary, right? And we're going to do the same thing for the next byte then. So we're going to give it like one extra byte. We're going to start again, let's say with 41, 42, 43 until we get to AF, right? So we've guessed the second byte, and we're going to, guess the rest of the canary in the same way by essentially just feeding it like one extra byte and seeing whether or not it crashed. And if it didn't crash, we guess that byte of the canary right. If it did crash, then we know we need to keep iterating. Right, so that's pretty awesome. Right, so if you have a canary, well, this is one way that I can brute force your server to figure out what this canary is. Right, so the question is, after 16 to 8 times, the attacker will always find a canary. How viable is this? So how many bytes do we have? We have 4 bytes, right, that we need to guess. Right, and with like probability on our side, we can do pretty well. Yeah, exactly, right. So like it is thousands of requests in practice, but it's actually not super bad. Especially if you're not targeting, like a serious player that would be able to detect these things. But even then, if you do it from different servers, like this gets pretty tricky to actually to figure out. And these things have been done in the wild. So can programs detect multiple consecutive crashes to prevent this kind of brute force attempt? Like how the iPhone locks you out after a certain number of wrong guesses. Yes, you definitely can detect this, and we'll talk later during the network intrusion detection class, like what programs you might want to install to exactly guess these kinds of things, right? Like when we crash due to a canary mismatch, it's a very particular kind of crash. So you can write scripts around that would detect these things and shut down your server. But it is really tricky, right? Like if you have thousands of legitimate users, a bunch that are not legitimate, um, what you kind of like you could turn off your server, and maybe that's the right answer, but you also like need to like figure out like, okay, hey, like maybe I can just block the actual attacker, whoever they may be, instead of denying access to the rest of my users. And maybe that's my goal as an attacker, is just to take you down off the internet, right? So if I get enough of these IoT cameras to send these requests, I can take you off the internet that way. But maybe that's I guess that maybe you wouldn't necessarily go about it this way. You would now at least try to guess the canary. Okay, so is it possible to change the canary value during runtime? Yeah, so that's actually what I would do, right? So like when you fork, the first thing that you should do when you fork is go change the canary value, right? Like the reason fork doesn't have this baked in is because that would be a pretty weird semantics for fork, right? Like as the operating system, I don't know what a canary is, right? This is a compiler inserted, or a compiler instrumentation that has only application level meaning. Not all processes necessarily have canaries or want canaries, but certainly those that do, you can include this as part of your libc to actually do that on first fork. Yeah, so what about all canaries on inherited stack frames? That is a really good question. How would you go about doing that? That would get pretty tricky. So like my guess is that that's a really good point. That wouldn't work super well. I guess the assumption here is that your server only moves forward, or at least your worker does. It never goes back, but like the control flow of these programs can be super weird. So yeah, this idea of changing the canary on stack frame probably doesn't work. I think Adam has a good point. Okay, let's move on. All right, so we already um, kind of know quite a bit about stack canaries and how much they actually give us. I guess I'll take one more question. Let's see. Right. So oh wait, no, we already did that. Sorry. Okay. So let's move on to our next mitigation, which is having a separate control stack. So this is trying to solve the problem a little bit more fundamentally, right? Like stack canaries are very clearly just going to try to detect that an attack is happening. Why don't we actually try to prevent control flow hijacking from the start, right? So if we look at what's actually going on, well, the control data, in particular, return addresses, are stored next to user data, potentially untrusted data, right? Now, this is not exposed to the programmer. At least as a programmer, I don't really care about the program control in this particular way, or how the underlying machine or compiler handles this information, right? So like what I really care about is like I can access my arguments, and I can access local variables. I don't care where you store the return address, as long as the return goes back to the function that called me, right? So why don't we actually bridge this gap between the abstraction that we assume as programmers and the abstraction that is implemented by these compilers, right? So what we're going to do with a separate stack is we're going to have our user stack, which is basically untrusted, right? And here is where we're going to store our arguments and local variables, but we're going to have a completely different stack, namely the control stack, where we store our, say, EVPs and return addresses, right? So now, like, if there's any shenanigans happening here, well, it can't affect the control stack. It can't overwrite the return address because it's a completely different stack, right? But we're, of course, going to have this separate stack pointer ESP prime, and how you do that in practice kind of varies according to the implementation of the separate stack that you may have. Right, on new Intel machines, at least the ones that will be coming out maybe this year even, there is a separate register for what's called the shadow stack, which is pretty much the control stack that we have here. And you as the programmer don't have, or at least like overflowing this stack won't affect this stack at all. And instead you have to use the SSP register, which is automatically handled by call and return, and it's compared against well, it will let you essentially detect things. So it's a little different, but close enough. So like the main point I want to get across is that you have a separate stack pointer, and you have to basically keep this one and this one in sync to make sure that your control and data are pointing to different stack frames. Okay, another abstraction that kind of works in the same, right, great. So that's a really good question. So can someone find the location of the control stack? We're going to get into that in roughly 1 or 2 slides. So the other abstraction is the safe stack. So here I'm pretending that we have some reasonable way of implementing it. So the idea of the safe stack is we're going to still leave the control data and at least safe values like local variables and arguments that are completely safe, so that it basically values that we don't take the address of, or buffers, right? So they can't be mucked with if we had a buffer overflow. So we're going to have a nice safe stack, and then we're going to put all the garbage on an unsafe stack. So we're going to have a separate stack that we're calling the unsafe stack, and this is where we put things that may be forged or overflowed. So if we have a buffer overflow, sure, this buffer might overflow something else on the unsafe stack, but it can't directly hijack control flow by overwriting a return address. So where is the information on ESP prime stored? So in both of these cases, something has to maintain this. So we're going to have to use potentially a separate register to keep track of this. And we're going to have to figure out, okay, like where is this stack, right? So where is this control stack? Where is this unsafe stack, right? So if we look at actual implementations, there's no actual separate stack, right? We have our linear memory, and we have load and store instructions to this linear memories and push and pops and calls and returns, right? So what we actually do when we implement these abstractions is we essentially put the safe or separate stack in a random place in the address space and hope that you can figure out where it is, right? So that's like kind of the assumption of these separate stack implementations is that the location of the control or the separate stack is actually secret. Now, it turns out that if you can figure out where this separate stack is, and you have an arbitrary, write gadget, then suddenly you can overwrite again the return address, and that would be, pretty bad. But the hope is that that's not super likely. In practice, it kind of is actually not that hard to carry out these attacks. What you would get, and I mentioned this very briefly, is in upcoming, at least Intel chips, there's this shadow stack, and that has a completely separate register. And the idea is, you can't write to this shadow stack directly. So it looks more like an actual separate stack. It's still in your address space, but it's basically a memory region that you can't write to directly. And with a little bit of hardware help, this also is like way faster because we're not suddenly using or reserving another register for this control or safe stack. We have actual hardware that will help us here. Okay. Maybe a pro route we can take this offline just in the interest of time. But I think the location basically has to be at a randomized address. Otherwise, we have no way of really reasoning about it without adding a lot more instructions between each stack operation. Okay, but we have these safe stacks. Okay, so how do we defeat them? Well, like Nicole said, well, if we can figure out where it is, we can overwrite to things that are on that stack. Another way to do it is you find a function pointer and point shellcode, point that function pointer to shellcode, and just continue executing the piece of code that would call this function indirectly. Okay, so kind of this gets at like another technique that we want to talk about is, well, I as an attacker, what I want to do is I want to point either return addresses or function pointers to my shellcode, so you suddenly start executing my code instead of the code that the program originally intended, right? So how have we been doing this, or like what's been kind of the approach that we talked about? Well, the easiest way, and the way we talked about, is just write your shellcode on the stack and have one of these pointers point to the instructions that are living on the stack. Now, the idea of WXRX is to prevent essentially these class of attacks, right? So like what we want to make sure is that even if you bring your shellcode and put it on the stack, we won't execute this thing, right? So what we're going to do is we're going to mark the stack as not executable memory, and then we're going to use the MMU, so that's the underlying hardware, the memory management unit, to ensure that whenever we try to execute instructions at stack locations, we're just going to trap and fail, right? And you might have come across this, or maybe you will if you do a little bit of searching. If you end up seeing XN or DEP, they mean the same thing. So kind of the idea behind WXRX is we're going to want to have memory that's either writable or executable, but not both, right? Because if we can write to memory that's executable, as an attacker, that's super dope. We get to do whatever the hell we want. Okay, so let's look back at our memory layout for x86 32-bit. And now we're going to assign some permission bits to all these different segments in memory. In particular, what we're going to do is we're going to mark the user stack as readable and writable, but not as executable. Shared libraries we're going to mark as readable and executable, right? Like we actually want to execute that code. The heap is similarly only readable and writable. There are plenty of attacks that would take advantage, of overflows in the heap and try to put code there. We want to make sure that you don't execute that code. But we can execute, code that's actually in the text segment. Let me get rid of this. And we want to make sure that we can write and read from the data segments. Okay, so the only executable bits are shared libraries and our text segment, right? Which now suddenly makes it much harder for me to bring in code here or here and point a function pointer or return address to one of these data buffers that's handling untrusted input. Okay, so what would this now look like when we look back at our example? Well, we have our buffer and overflow our buffer, and we're going to overflow and even point the hijack return address to our beautiful shellcode. Well, once we execute this ret instruction, the EIP will point to this address, which will be somewhere here in the user stack region, and we're going to crap out, right? The MMU is going to say, sorry, I don't execute code at addresses in this region, right? So this is pretty awesome. Now we can't bring in shellcode. That's much, much harder now. But like as an attacker, I have to do quite a few more things to get the program to execute whatever I want it to. Okay, so what are some trade-offs? Well, this is super easy to deploy because we don't have to do anything. We don't have to recompile our programs, right? This is a linker thing, and it can be done pretty easily. It's also super fast, right? Like it's enforced in hardware. This unfortunately does have a downside. If you're on a tiny embedded device, you don't have an MMU. The MMU is typically used for virtual memory, and we're going to talk about virtual memory later. If you haven't seen virtual memory, I think it's worth looking up because this is going to come up again and again. So what this means is on embedded devices, we have to do something else. Realistically, if you use the same piece of code, you won't do anything else. So you have, the problems that you would back in the early 90s. Now, there is another trade-off, which is that some pages need to actually be both writable and executable. What are some examples of programs that need both writable and executable memory? Yeah, JIT compilers or something. Right, so browsers need this, right? In particular, browsers, right? Like they take, I have server, browser. The first thing that I do is I take a bunch of JavaScript from some remote server. I parse it, I then compile it, and then I start executing it, right? Like, okay, like you can just interpret that code, in which case we don't need writable and executable. Modern browsers have really complicated JavaScript runtimes, and they have a built-in compiler which would take this, JavaScript code and compile it to native code, which means we have to be able to write to memory and then make sure that that memory is actually executable, right? Typically, the way we do this is we write to memory and then we turn on the execute bit. But it's definitely like one of the cases where like we have to have the ability to turn on these write execute bits. Okay, and Okay, so now it's much harder for us as an attacker to bring in code. Can we somehow still defeat WXRX? Well, okay. The first thing that we can do is like we can still write, whatever we want to the return address stored on the stack, which means that if we have some gadget within our address space, we can just write the address of that gadget and have that function, when calls ret, jump to that gadget that might execute things that we care about. Okay, in practice, right? So like we already kind of saw this in the last class where we overwrote the return address to jump to Baz or to Funk. I forget which one, but that's essentially what we ended up doing. Now, this kind of attack approach is called return into libc attacks because most of the time you don't jump into parts of the program. You really jump into parts of the standard library, namely libc. Right, so like libc has functions like system, which take an argument. In particular, a system just takes a string of the thing to execute. So if you give it bin bash, now you suddenly have a shell that you can use as an attacker. Right, so our goal is to kind of take these return to libc ideas and modify our exploits to jump to these parts of libc and let's essentially execute the same code we would have otherwise by bringing in shell code. And the thing that we're going to try to do is we're going to try to execute the system call with bin sh so that we get a shell. Now, before we do that, I wanted to just bring up again like what a normal or what the stack looks like as we're about to call system, right? So when we call system at the beginning of system, our stack pointer points to the top of the stack, which means we have our return address where we return once we exit system, and we have then the command that we pass to system telling it to execute, right? So and cmd might point to bin bash, right? So some string is somewhere in the address space where the string bin bash is, right? So this is what the stack frame looks like. It just takes one argument. This is that argument. And this is what system expects when it starts doing its thing. Okay, so this is what we're going to try to make the stack look like when we overflow a particular buffer. So going back to our kind of canonical stack, we have our buffer here. We have our saved EBP and our return address. I color the return address in red because that's the thing we want to really pay attention to. So like our goal here is to take this function and redirect control flow to system instead of return wherever this function may have been called from. Okay, so how do we do that? Well, let's just clear out everything else so we can just focus on the stack and how we're going to overflow it. So the first thing we're going to do is we're just going to go just overflow the buffer until we get to the return address. Okay, then what do we do? Well, we overwrite the return address to point to system. Suppose we know where system is actually located. Then we're going to give it where system should return. So we're just going to tell it that like, hey, the thing that actually called you is the start of exit, right? This is a lie. We want the program to exit cleanly. And then the first argument to system will be CMD, right? So we're going to ideally just have that thing point to whatever our attacker script is. And we're going to do that in the next set of bytes, right? We're going to just essentially include that in our payload and have CMD just point to this part of the stack where the string bin sh is actually stored, right? So we're going to keep executing parts of this function. Right, we're done overflowing the buffer. Now we're about to exit the function and jump to system. So what happens? Well, we're going to execute leave. Right. So what does leave do? Well, it moves EBP into ESP. Right. So ESP is now going to point to the same thing where EBP points to. Then we're going to pop EBP. Right. So we're going to store that question mark into EBP and change ESP to point one up. Right. So now ESP points to the top of the stack, which looks like the system thing there. Then the next instruction that we execute is a ret. What does ret do? Well, it takes whatever's at the top of the stack and puts that into EIP, right? It jumps to EIP. So we're going to actually execute that, which means now ESP points at the location where we have, exit and CMD and so forth. And EIP is now pointing to the start of system, right? So now we're starting to execute system, and to system, this is what the top of the stack looks like. We have the place where we should return. We have our first argument, and honestly, we don't even care about that. What we care about is what the first argument tells us. It just tells us that, like, hey, your string is actually just like a little bit below you on the stack, right? So going back to where we started, well, this just looks like a normal function call, right? So we have our save return address, which is our exit. We have our first argument, which is the pointer to command, and command just happens to point to this thing here. So now system starts doing its thing. It just looks at whatever's at the top of the stack, and it executes, it creates a shell for us and points it to bin sh. Okay. So this was like a little complicated, but kind of the whole point that we're trying to, or like what we're trying to do is we're trying to jump into parts of libc. In this case, we're going to try to jump into libc where we're executing a syscall and creating where in particular we're executing the system function. And where we're going to do that is by aligning the stack so it looks just right. So it looks just like a normal function call to the function that we're redirecting control flow. In this case, that function is system, and the things that it's expecting on the top of the stack is one argument, which is a pointer to a string of the thing that it should be executing. Okay, but you may say, cool, but I want to execute actual shellcode. I don't want to execute system. If we're thinking about a network attacker, executing system with bin sh doesn't give me a shell. I want a remote shell. I still want to bring my own code that creates a socket between me on one end of the network and your machine, and give me a shell that is remote, not something local where I can't do anything with it. So how can we still bring shellcode now that we've disabled executable stacks? Well, we can just inject code, right? One thing that we can do if we have the ability to carry out these return to libc attacks is one thing we can do is we can, instead of calling system, we can call mprotect. What can we do with mprotect? Well, we can turn on, we can make the stack both writable and executable, right? So mprotect lets you essentially do this, right? It lets you change the permission bits on a region of memory. In practice, if you look at like the systems that people attack, which are things like browsers and web servers, these things have just-in-time compilers, which means that they're taking data and that data becomes executable code. So as the attacker, the thing that I would do is essentially just, when I ship code to your browser, just ship a ton of code. So that now like there's a lot of code in your memory address space, and then I'm going to overwrite some code pointer to point to some random locations with the hope that it will land on one of these chunks of codes that I've sprayed in your heap. This is why it's called JIT spraying. Okay, so what does this code look like? Well, if we want to just look at like a little bit of JavaScript code, you can write code that looks like this. You can declare a bunch of variables, then assign essentially a bunch of constants to these variables. And those constants, when you look at like what they look like in the memory, they look like those instructions there. So pop EBX, ret, pop ECX, ret, so on and so forth. And these will be gadgets that we'll be able to actually use as the attacker to, like, if we could somehow jump here, then we're able to actually do whatever the hell we want. So it's just another way of bringing in shellcode. Okay, so I recommend looking at this paper if you're curious about these things. It's still kind of a really interesting arms race, but basically, like, this is a pretty powerful way of carrying out real attacks. Okay, so in the remaining time, the thing that I want to talk about is ASLR, or address space layout randomization. Now, if we step back and think about, like, well, what's going on? Well, if we look at the exploits that we've been looking at, these exploits basically need precise addresses, right? So the stack-based overflow, we need to know the location of the shellcode. The return into libc attacks, right? Jumping into system, we need to know, where system or any of the library functions that we want to call. So the idea of ASLR is, well, we're going to add a little bit of offset to where the stack is located, where the shared libraries are located, where the heap, text segment, even data segment, where all these things are. We're going to like slightly move them up or down to make it harder for the attacker to guess the location of either the shellcode or the libc, so that if they were to try to overflow one of these buffers, they'd have a really hard time actually doing something productive besides crashing the program. What does ASLR look like? Well, how much you randomize and which bits you randomize vary according to systems, but what we're going to talk about for this class is the 32-bit PAX ASLR, which randomizes the stack by 24 bits. So we fix these bits here to 0, and the top bits, we fix them to 101, and the rest of these bits, these 24 bits, we're going to just assign random values to. So this is like where the stack actually starts. The mapped area or the shared library area, we're going to randomize 16 bits. So we're going to fix the bits on the bottom there, and we're going to fix, again, the top ones here. And then finally, for the start of the text segment, we're going to, again, randomize 16 bits and keep a bunch of the most significant bits and least significant bits fixed to zeros. Right. So we're randomizing the stack by 24 bits, the libc or mapped region by 16, and text segment by 16 bits. Now, what are the trade-offs of doing this? Well, first, we actually need to change how our programs behave, right? Or how they're compiled. So first, we can't use absolute jumps if things move around, right? Our program has to be robust to that. Which means that we can't use absolute addresses, which means that they're slightly slower because we may have to have an indirect or relative jump. Nowadays, this is actually super fast, but it's something to be aware of because it took quite a bit of time to get here. Right, the whole process layout has to be randomized, so the compiler has to change, the linker has to change, the loader has to change, kind of everything actually has to change. This was pretty intrusive, but nevertheless, I think a worthwhile mechanism that at least raised the bar for a while. Like nowadays, actually bypassing ASLR is not super hard, but at least for 10 years or so, it was a pretty useful mechanism in practice. And you should still use it because honestly, like it prevents, the script kiddie style attacks. There is overhead, right? Because we're moving things around. There's also an increase in code size. The upside is because we're randomizing different segments, we don't just get the benefit for stack overflows, we get heap-based overflows too. 1 second. All right. So the questions that we're going to want to try to answer is, when do we actually randomize? Right? Do we do it at boot time, at compile time or link time, at load time, at runtime? Do it on every fork? And what's the trade-off of these different things, right? So for a while, all we did was randomize at boot time. But nowadays, actually, whenever your program starts up, it starts up at a different location, and the different segments that we randomize will vary as well. So for a while, we didn't randomize the text segment. That turned out to be a bad idea. And nowadays, we randomize that by default as well, right? And the trade-off is basically performance, right? Like with the more we randomize, naturally, the more performance impact that would actually have. Right? Think about like randomizing the kernel. That's not actually super trivial to do, right? Because the kernel starts up at a particular location, and trying to move it later, like, will be pretty complicated. And like we're still trying to randomize the kernel. It's not in a great state. Okay. The other thing that we've been talking about is how do we defeat these mechanisms? Well, okay, if we have binaries compiled with fno-pi, which was the default for a while, nowadays pi is actually enabled by default, then the location of the address and the data segments would be in the same place, and this is actually like enough to carry out most realistic attacks. So like you really want pi turned on by default. So pi stands for opposition independent code. Okay, but what we're going to do is we're going to try to carry out an attack where these things might actually be randomized. And what we're going to do is we're going to take advantage of the fact that where the region is located in memory is random, right? So it's at a random offset, but what's inside that region stays the same, right? So the layout of each region is actually the same, even though we may have a slightly different base address. And what this basically means is that if we can figure out somewhere, say in the map region or the libc region, where a particular function is, then we know where the rest of that particular region or what the rest of that region looks like. So getting some information leaks basically the base address, which leaks everything else. And for 32-bit binaries, at least, we're able to carry out brute force attacks and figure out what these regions look like and take advantage of that to come back to our return to libc attacks. For 64-bit binaries, brute forcing doesn't actually work, so we can't flip that many bits. But heap spraying works pretty well. So it's similar to JIT spraying. It's kind of the same idea. We just spray the memory address space and try to jump to locations, and with enough probability that will succeed. Okay, so let's take a look at how we de-randomize ASLR. As an attacker, our goal is to call system with an attacker argument. Our target, again, is the Apache web server or the Apache daemon. This thing actually had a buffer overflow in AP get line, which gets a line from a remote location. It looks something like this, where we stir copy, some user control string into buff, and buff has, 64 bytes. So this was an unchecked stir copy. And we're going to take advantage of it, right? Like, I think the thing to point out is that Apache is a web server, so it has a bunch of security mechanisms turned on. In particular, we're going to have WXRX enabled, and we're going to have ASLR enabled. The one thing to note about ASLR is that whenever you fork a child, that the address space of that child is exactly like the parent, right? So it's similar to how to what we said about canaries, like the memory is going to be identical, which means that the offset of these different things will be in the same location. And when we crash, we again, get to retry, right? So we're going to kind of carry out a similar attack to the one we saw earlier. But in this case, like, our goal is to figure out where different parts of the address space, or at least libc, are, so that we can carry out our control flow hijacking attack. Okay, so there's really two steps to this attack. First, we're going to find the base region of the map region, right, where libc essentially is. And stage 2 is we're going to call system with a command string. We already saw stage 2 earlier when we overflowed, when we just talked about return to libc attacks. So for the rest of the class, we're just going to talk about this, and maybe next time or in section, we can, or office hours, talk more about this if there are any questions. Okay, so how do we find the map region? And this should be pretty quick. Is, well, again, the layout of the region is fixed. So what we're going to do is we're going to overwrite, say, the return address, the red thing here, with a guess to one particular function in this region called usleep, right? And once we figure out whether or not that particular function is actually usleep, then we know from just doing a little bit of arithmetic where usleep is in libc, and then we're going to be able to recover where base is. Then once we know where the base of this libc region is, we can figure out where system is and carry out our remote shell creation attack. Okay, so let's actually do this. How are we going to do this? Well, we're going to overflow our buffer with a bunch of stuff, and ideally what we'd like to do is try to figure out where usleep is. So we're going to give an address that points to somewhere near usleep. Now, if we guessed usleep, the address, right, then what we know is that the freezer will freeze for like 16 seconds because of the additional arguments that we pass to usleep. So we know that the server will freeze for a little bit. It's sleeping, and then it will crash. If we guess the address of usleep wrong, then it's likely not going to have the same delay. So it's not going to sleep at all. It's probably going to crash almost immediately. And we can tell, based on that alone, how long it took for the server to respond, whether or not we guess that address right. So if we guess the address right, then we know where usleep is. From that, we can figure out where system is, overflow the buffer again with system, with the location of system and arguments to the command of your choice, and voila, you're done. Now, It will take quite a bit of time for you to do this, but if you look a little bit of like what is the probability of success, um, well, we're going to have at worst, 65,000 tries. But the good bit is that we don't actually have to randomize things like the stack, because usually you just pass in string arguments to the stack, and there's usually pointers in there where you can have your command payload. Okay, so that's all we're going to talk about for this particular attack. For the system call bit, it can get it's basically the return to libc that we saw earlier. In the paper that we reference, it's a little bit different. It's a little bit more complicated, but the idea is the same, right? Like you basically want to make sure that the call to system looks something like this. Okay, so if you have to take off. We are actually done with all our mechanisms. In the actual slides that I posted online, we go through the second step, but it's basically the same thing that we went over earlier. Okay, so Joshua has a question. Do ASLR systems have mechanisms to monitor the number of new children forks created? So ASLR is kind of now built into, like Linux and Windows and OS X. We don't keep track of, how many forks. I mean, I guess we do. Your OS definitely does this, but it doesn't keep track of whether or not that thing has crashed and whether or not it should randomize on fork. Again, it's similar to the canary problem, but this one's actually fixable. We can randomize on every fork. I don't think any server actually does this, but they really should be doing this. Yeah. If there are any other questions, I can stick around, but there's no obligation. Y'all should just take off and go do fun things, and rewatch parts of this if you didn't catch certain bits. Okay, so Jason, can you go over high level how ASLR works? So the basic idea, again, is like we're going to randomize the location of the text segment, the libc segment, the stack, and so forth, to make it harder for the attacker to guess addresses, right? Like in all the attacks that we've seen, we largely know where this shellcode might be, or where the location of system is, right? If we're doing return to libc attacks. If suddenly, as the attacker, I don't know where my shellcode is, or I don't know where system is, like it's much harder for me to carry out a real attack, right? So kind of the idea is like, okay, if we make this hard enough, in particular, like, okay, for 32-bit, it might not be hard enough, at least in the Apache case, but for 64-bit is actually pretty hard. So like we can't guess, and now suddenly a bunch of these attacks just go away because as the attacker, I can't craft a useful payload that will jump to my code. All right. I will do one more quick question and then let y'all take off. All right. Let's actually call it. Thanks for sticking around. I'll see you next time.